So first, it's helpful to kind of go back to a few principles of ray optics and talk about what happens if a light ray enters into a material. So let's start with some ray of light that is entering from air into glass at a perpendicular angle of incidence. So there's a right angle between the direction that the ray is traveling and the surface that it's entering into. So here, the air has some index of refraction n1, and the glass has some index of refraction n2. So in this case, when we have this light ray that's entering into this glass, we will just see the light ray kind of pass straight through without deflecting at all into the glass. However, if we look at what happens if a light ray enters into glass at a more general angle, we can also predict what's going to happen to the output rays in this case. And light entering at a general angle is going to transmit or refract and reflect according to two principles of physics. One is Snell's law and one is the law of reflection. So here in this diagram, we've introduced some angles. We have theta I, which is the angle of incidence, the angle between the direction that the light is traveling with respect to the perpendicular to the surface. And we have theta T, which is going to be the angle between the transmitted light ray and the perpendicular to the surface. And then finally, we also have theta R, which is the angle between the reflected light ray direction of travel and the perpendicular to the surface. So what the law of reflection tells us is that theta I, this angle of incidence, will equal the angle of reflection. And what Snell's law tells us is that the index of refraction n1 of the material that you're coming from times sine of theta I, which is this angle of incidence, will equal to n2, the index of refraction of the material you're traveling into, times sine of theta T, which is this angle that you're transmitting at. So if you know n1, n2, and theta I, then you can solve for theta T and find what this transmitted angle is going to be. So we might ask the question, is there ever going to be a condition under which we only get reflection and we can't get any transmission of our light? So it turns out, in some cases where you have a large enough theta I angle of incidence, and when you also are traveling in a higher index of material and reflecting off of a surface that is against a lower index of refraction material, in some cases where these conditions hold, you can have something known as total internal reflection happen. So what is total internal reflection and how does this happen? So if we picture theta T, which is the angle of transmittance, we can think about the case where what if theta T was so large that it was 90 degrees? So in this case, what we would picture of happening to this transmitted wave is we would picture it somehow propagating basically perpendicular to this surface boundary. And this might start to seem a little bit weird because we might start to ask, like, is it even transmitting in that case? Like, so this is going to happen and we can also ask what's going to happen even if this theta T is even greater than 90 degrees? Like, how do we even interpret what's happening to the light in that case? So when this happens, this happens when we take Snell's law, we take theta T and we set it equal to 90 degrees or greater. And this would mean that sine of 90 degrees would be 1 or greater. So this means that this condition for when this total internal reflection will happen is going to be n1 divided by n2 times sine of theta I greater than or equal to 1. So in this case, we can just say, well, it seems like the light isn't going to transmit at all. So all of the light will just reflect. And basically that is kind of what happens. So this is how, like, a lot of this is actually like a very useful principle, and it's how like fiber optical cables can trap light. But technically speaking, it isn't quite true that nothing transmits at all. So in actuality, when total internal reflection happens, even if theta t is greater than 90 degrees, there still exists a solution for this transmitted light, but it's no longer really a light wave, and instead it's going to be an exponentially decaying field. And this is called an evanescent light. So how does this happen exactly? Well, we can think about light as traveling according to an equation for the electric field of the light, where the electric field goes by e to the I kx, where k is your wave vector relating to your momentum of your light, and x is just the position of the light. So if we look at the case of light that's potentially going to be transmitting in the case of total internal reflection, we know that we can calculate the component of the light that's going to be transmitting perpendicular to this surface boundary between the glass and air. And that component of that k vector is going to go by cosine theta t k. So we know from trig rules that cosine of theta t is equal to the square root of 1 minus sine squared of theta t. But as we just mentioned from this previous slide, because of Snell's law and because of what happens in the condition of total internal reflection, sine squared of theta t, sine of theta t, and also as a consequence sine squared of theta t is going to be greater than 1 in the case of total internal reflection happening. So this means we can already see that this portion of our k vector, which is somehow kind of transmitting perpendicular to the surface, is going to have to be imaginary, because the square root of 1 minus something greater than 1 is an imaginary number. And we can kind of explicitly show this by taking an imaginary number and multiplying it by our square root and rearranging the terms inside of the square root. So now that we know what cosine of theta t is in this case of total internal reflection, we can plug that back into the expression for the wave. And now we have two imaginary numbers that multiply by each other, and we just get -1. So this just means that we will just have a decaying exponential now. So keep in mind that this decaying exponential decays on the order of magnitude of the wavelength of the light. So in the case of like visible light, this would be a very small distance. This could be like hundreds of nanometers. So this means that it's not like this light is traveling really very far if it's has a very small wavelength. Now to talk about frustrated total internal reflection. If we bring another glass triangular prism very close to this first glass triangular prism, we can actually kind of frustrate the total internal reflection and prevent it from fully happening. And by very close, this means, of course, again, this order of magnitude of the wavelength of the light. Because if you aren't that close, this evanescently transmitting light will basically decay down to 0, and you won't be really transmitting very much. But basically, by bringing this second pane of glass closer to the first pane of glass, you can now allow for some of this light to transmit. And this is how these cube-based beam splitters work. So the layer in between of resin or glue is the order of magnitude of the wavelength of the light, and you can tune it so that you can actually control how much of this light will reflect and how much of the light will transmit. Since, as we mentioned at the beginning, these beam splitters will conserve energy, so the sum of the intensities of the transmitted and reflected beams of light have to sum to equal the original intensity of the entering light ray. So we could imagine starting with these two panes of glass where there's no gap at all, they're like pressed up against each other. In this case, you'll completely get transmission of light, And as you pull the second pane of glass further away from the first pane of glass, you'll start to get some of the light being reflected. And the height of the light wave that reflects will increase more and more as you pull the second pane of glass further and further away, until you've basically kind of completely gotten rid of this second pane of glass, and now everything reflects, and you recover this case of total internal reflection. So if you think about this a little bit, it might start to seem a little bit spooky, because we might start to ask, well, we know that energy is conserved, and like I mentioned, like somehow the height of this reflected beam of light has to depend on the location of the second pane of light that we're moving further away or bringing closer. So we might ask, like, well, how can this even happen, that this reflected light knows about this other pane of glass? But it turns out that there's an answer which isn't actually very spooky at all, and the answer is that the reflected light knows about the other pane of glass through destructive interference from back reflections. So let's take a closer look at this. So if we take a closer look at basically these two interfaces where the light is transmitting and reflecting, as the light is entering from glass into air, and then as it enters from air into glass again, some of this light is actually going to be reflected, and some of it will be transmitted. So, and then as this reflection bounces back and then bounces back again, some of this light will be transmitted and some of this light will be reflected. And this will kind of go on and on and on, basically forming an infinite series sum. So the size of the back reflections will decrease as you increase this distance between the two panes of glass, because this light was evanescently decaying while it's in this gap region. So it might then seem like, well, as we take the second pane of glass, move it further away from the first pane of glass, we should be getting actually less and less reflection somehow, not more and more reflection. So, but we also know that when the second pane of glass is moved far away from the first pane of glass, we're supposed to be getting the most reflection possible. So the way that this is possible is that these back reflections are largely destructively interfering with the initial reflection. So this initial reflection is going to be the strongest reflection with the most amount of light kind of inside of it. But these back reflections will destructively interfere with this first reflection. So actually what will happen is as you bring the second pane of glass further and further away from the first pane of glass, you'll get less and less destructively interfering back reflection, which will actually build up this intensity of this reflected beam. So there's kind of a nice paper which goes through this, which I've included a citation for in the center of this screen here. And you can also look at, you can also kind of plot what this total reflectivity of this beam splitter will be by summing this series, where the series has the electric field that is reflected and of each consequent back reflection. And if you sum that and you get the total reflectivity, you can plot that as you're with the increasing gap size between the two panes of glass. And you can see that when these two panes of glass are basically just completely squished together with no gap, basically, we will have zero reflection. Everything just transmits through. But as you slowly start to pull this second pane of glass further away from the first pane of glass, you'll get more and more reflectivity until it approaches 1.